Okay, so we often talk about heat and temperature almost like synonymously. It turns out that these two terms are often confused a little bit. And so we're going to really identify right now what heat is in this little mini lecture. And we've talked about temperature in a previous mini lecture, so make sure you go back and check that out. We're going to talk about how heat is defined, how we measure it, and do a fun little example on heat. So heat is defined as the transfer of energy between two objects because there's a temperature difference. So as a result of a difference in temperature. Okay, so that's how we're going to define heat, this change in energy, this transfer of energy. Now we talk about heat flowing from one object to another, but I just want to be very, very clear. Heat is not a fluid in the sense that fluids flow, and it doesn't follow fluid dynamics that we've kind of talked about in previous mini lectures. But we still use that terminology. So just use some caution with that when we talk about heat flowing from one object to another. I want to think about it as it certainly is a transfer of energy from one object to another. And so that's okay, but don't think of heat necessarily as flow. Now, we actually use multiple units to describe heat. So we're going to go over each one of those units. The first unit that you'll hear in description of heat is the calorie. Right? So the calorie, lowercase cal, is how much energy is required, how much heat needs to be transferred, how much energy required to raise 1 gram of water by 1 degree Celsius. Okay, so to raise 1 gram of water by 1 degree Celsius. Now that is a really small amount. So similar to grams to kilograms, when we talk about calories, we often use kilocalories as our kind of base unit when we talk about calories. That actually is, this is where there is a little bit of weird confusion. This is a calorie with a capital C. Okay, so calorie with a lowercase c, raise 1 gram of water by 1 degree Celsius. Calories with a capital C, that's what energy is required to raise 1 kilogram of water by 1 degree Celsius. Okay, capital C calorie is what we see when we talk about the energy of food. Okay, so that's that energy value in food. That's the capital C kind of calorie, so a kilocalorie. All right, that's one unit we use to talk about heat. Another unit that we use to talk about heat is the British thermal unit. And this is what's affectionately called a BTU. Okay, so you've heard of BTUs perhaps when talking about heat. Now, a BTU is the energy that's required to raise 1 pound of water by 1 degree Celsius. So that's what a BTU is. So we talk about heat in calories, we talk about heat in BTUs. Now it turns out that heat is, in fact, a transfer of energy, and we've talked about energy before in the terms of mechanical energy. So there's a third way where we talk about heat, and it's the mechanical energy equivalent. So it's a way to talk about heat in terms of what we think about in terms of mechanical energy, or the joule, the mechanical equivalent unit. So you've heard about joules before in our discussion of mechanical energy. So it's the joule. Now, it takes 4.186 joules to equal 1 calorie, lowercase calorie, which is 4.186 kilojoules for 1 capital C, 1 kilocalorie. All right, so that's an equivalence that we're going to be using kind of as we look at mechanical equivalent of heat and sort of this more commonly used measurement of heat. Okay, so let's look at a fun example, kind of looking at mechanical equivalent of heat and the calorie. This again is just sort of your brief introduction to what heat is. Okay, let's imagine that you are eating some cookies. And you eat one of those 100 calorie packs, you know, those things that we think, oh, it's only 100 calories. I can eat a little 100 calorie pack of cookies. And then you go and you think, well, I'm just going to go jump on my stair stepper and I'm going to do a whole bunch of stairs until my stair stepper tells me I've burned 100 calories. Well, how does it know how to do that? All right, so I'm going to give a little caveat here. There is an efficiency, meaning we actually aren't burning the same number of calories we're intaking when we just do stair stepping, but we're going to use it as a fun little exercise. See what I did there? As a way to look at this mechanical equivalent of heat. So let's say we eat 100 calories of cookies. How many stairs do we have to do? Okay, so stairs, that's moving up granted, admittedly, on a stair stepper, you don't go really anything in altitude, but we're going to pretend that we do. That's moving up in altitude, and it takes us work to move up in altitude. So if we remember our relationship for work is going to be our change in energy, right? Work is our change in energy. And in this case, it takes so much work to change our potential energy. So this is going to be a change in our potential energy. And so just as a reminder, it's gravitational potential energy. Okay. And so this is our mg delta h, that change in height. Okay. Change in altitude, change in the number of steps that we do. Okay, so we're going to make a few assumptions in our fun little exercise. We're going to say that our mass is 60 kilograms. All right, and that one step is, is equal to 0.3 meters. So about a third of a meter is a step. Let's just say a step's about a third of a meter. Okay, so the first thing we want to understand is how much energy in terms of joules, the mechanical equivalent of heat, how much energy is in 100 calories. Now we want to remember that 100 calories, capital C, is equal to 100 kilocalories, right? 100 kilocalories. We know that 100 kilocalories, in 1 kilocalorie, we have 4.186 kilojoules of energy. So that is 418.6 kilojoules of energy needed, or that we've consumed. Okay, so 4.86 kilojoules of energy, which means we need to do 418 I don't know where that came from, 418.6 kilojoules of energy, which means we need to do 418.6 kilojoules of work to burn off that energy. All right, so that means that our work is 418.6 kilojoules. That equals mg delta h. So let's make sure our kilojoules is in proper units so that we can do the proper division. So we have 4.186 times 10 to the 5th, so 1, 2, and then 3 more with kilojoules, joules, is equal to our mass of 60 times 9.8 times our change in height. And we find our change in height to be 711 meters. So 711 meters is our change in height. Now, if our change in height is 711 meters and one step is 0.3 meters, how many steps do I need to do? Well, we have 711 meters and we have 0.3 meters per one step. That gives us a total of 2,135 steps. Woohoo! All right. So just the use of this equation, fun little example to do that. Turns out that's only if we're 100% efficient and all of those calories goes into the number of steps. That's not actually what happens physiologically, but it was a fun way to sort of explore our connection between mechanical work and heat and just getting used to looking at the units. All right, good job.